to this Learnathon. We had about a little bit about the fundamentals of machine learning, and that was recorded. It was put on YouTube channel of AI Eswatini. So if you missed that, I encourage you to watch the recording that was put on the YouTube channel. And if you have any question, please put it in the chat. And today we're going to be with Anthony Gitau, an AI engineer from Kenya, and he'll be talking about building practical AI skills, building practical AI skills. I can see he's here. You're welcome, Mr. Anthony, and everybody. You're all welcome. I hope you have a wonderful session. Engage through chat as you raise questions. There'll be people to answer you, and even after, I think we will have a Q&A session for Anthony to answer some of the questions that you'll be having. So, not going far, please welcome Sir Anthony. The floor is yours.
Thank you, Betsy. Yeah, I'm super pumped to be here. Yeah. Thanks, Sam.
We cannot hear you.
You can't hear me. Okay. Can you hear me now? Not yet. Can you hear me? Can you hear me?
Yes, I can from my side.
Awesome. You can hear me. Okay, cool. Awesome. Yeah, that's great. So yeah, you know what? I'm just gonna try to share my screen so we see if you can see my screen. Hit share. Share. Learning fundamentals, and then I can do a slideshow. And then we'll see. So is my slides up? Someone just, do you see it on your side? Do you see my slides?
Yes.
Awesome. Okay, so I was invited to talk about some deep learning fundamentals. Yeah, and I thought I thought about it, and I'll try to talk a little bit about my experience and some of the things that I know about deep learning. So welcome this to be a discussion. So feel free to just contribute on the chat, or just feel free to correct. The middle, so just try to see if you just learn something. I hope I can be heard, right?
Yeah, sure.
Perfect. Very I hold a bachelor's degree in biomedical engineering. Across the way, I had some. Yeah, I'm just sharing knowledge. Yeah. Okay. So the talk about life. There's so much like any questions really. And then I thought I'd give you assignments because like Sam told me this is like 4 weeks or a little longer. So why not next week the speaker I will tell them to check the assignment. And hopefully there will be some resources that could be useful to yeah. If you feel like you want to post online, you can tag me either on Twitter or on LinkedIn. If you search these names, you'll find. How does that sound? Yeah, I just need to hear an echo back so I know I'm not alone. uh, yeah,
I
okay.
think
Then I'm
they're
looking at my
reacting.
slide. Okay, I see. It's interesting. Okay, because like when I move to my slide, I don't, I don't see the chart. I wish I had like, I don't have two screens with me at the moment. So yeah, okay, I have to like move around. Okay, but feel free to say yes. Just, but yeah, I'm happy. Okay, uh, I just wanted to start. Sorry, I just wanted to start by yes, please. Is a question. Okay. Um, has anyone trained a deep neural network? Uh, I think what can someone do? So someone can say on the chat, yes, no. I don't know what that is. Has anyone trained a deep neural network before? You can type on the chat. You can say yes. You can say no. You can say maybe. I'm not sure. Okay, a few yeses. Okay. Someone might learn something new today. Awesome. Okay. 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 A few nods. So hopefully we learn something new today. Okay. Okay. Cool. Cool. Okay. I see. I see. I see. I see. Has anyone taken a math course before? Uh, like a math, um, like a calculus, linear algebra, like a college. Yeah. Like I'm not sure. Okay. Okay. I think I have two questions. Okay. So people have taken math courses. Cool. 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 Okay. I see. I see. Okay. Awesome. Awesome. Has anyone done programming before? Like, describe the program language you're very like you could probably you use more like you've used in this week, something like that. The one that you feel a bit confident with. Any programming language? Any programming languages people are pumped about? I don't know, like Python, R, Ruby on Rails, Julia. Okay, cool. Cool. JavaScript, perfect. C++, terrific. Okay, nice. Um, awesome. Jax, anyone played with Jax? Oh, Java, I see. Awesome. Okay, perfect. Nice, nice, nice. Sounds good. I think feels like everyone is fired up. Uh, yeah, I see a lot of Java and C++ and Python. Okay, of course, Python means a lot. Okay, I see, I see. Nice. Okay, okay. Then I'll try to sort of talk from uh, first principles. Uh, and, and yeah, yeah. If possible, you can like mute yourself. That'll be cool. If you mute yourself, that'll be awesome. Is it? Yeah. Yeah. Perfect. Thanks. Yeah. Perfect. We'll try to get to the core of these concepts, not so fast and not so slow, hopefully. Okay, so by the end of this session, I hope you'll be able to explain some deep learning concepts. So what deep learning is, why it's useful, then you understand how neural network works. So Sam told me that last week we had like machine learning course. So I'll try to uh, just get deeper on the neural network parts. And then you'll be able to recognize some key components like layers, activation, loss functions, optimization. Yeah. And then you'll be able to appreciate some architectures and real world application. And hopefully, this is the fun part. You can play around with some code, and like be able to classify some stuff. Yeah. Um, yeah. Sounds good. Sounds good. Please ask me questions at the middle. Please just, yeah, just say excuse me, and then like I will give you a chance to speak. Okay. So, um, why deep learning? So, what you're seeing on the screen right now is so I got this from like someone's GitHub page, and they had shown how they had trained some neural networks to. On the right, you see it's recognizing. I do not can download my laser. So here you can see a neural network is recognizing digits like a 7, a 3, an 8, 9, and this is how an autonomous driving car sees the world. So it's like some blocks and some roads, some people, etc. And so the key insight for deep learning is that computers can learn representation from raw data and then be able to perform tasks. So the learning of representation is key. And so you can imagine things like here you can imagine things like ChatGPT, Gemini, Claude, all these things that um, all of this image classification, autonomous driving, these are things that these are applications that have been enabled by deep learning. Yeah. Uh, Maybe at this point I can ask how many people have played with Gemini in the room? Has anyone like typed something on Gemini? People know Gemini, right? Like you can type on the chat and say, yes, I played Gemini. Yes, I played with Gemini. Or does anyone know Gemini? Okay, perfect. Nice. Awesome. I love the yeses. Okay, perfect. Yeah, Gemini is cool. I love Gemini. You've not used Gemini. So just head on to Gemini.com. Just type it on your browser. Oh, even when it was called bad, it's moved so far. Yeah, right. Yeah. Um, if you've not used Gemini, just type on your browser like Gemini.com, and then yeah. So those are types of deep learning like applications we're talking about. And the insight here, the main point I want you to go home with is that like you're able to build systems that can learn to represent low data. So the goal is to represent data. So what you're seeing here, for example, an autonomous car is able to represent like the entire the state of a road. So there are other cars, there are pedestrians, there are sidewalks, there are signs, etc. On the right, and deep neural network is able to get a representation of how a 5 looks like, how a 6, a number, a digit. Okay, so what deep learning really is in this field called AI. Like you've probably heard a lot about artificial intelligence. So these are the techniques that enable computers to mimic human behavior. So we're able to essentially being able to make that human beings, the intelligence that human beings have. And here if you think about it like a concentric circle, like a circle inside the circle, machine learning is the ability to learn without being programmed. So the traditional way of writing programs is that you write instructions, like detailed instructions. If this happens, do this. If this happens, do the other. While this is going on, do something. Explicit conditions. But if you're training a self-driving car, it's it's impossible to outline all instructions on the road, right? Um, so machine learning is this domain or field or ability for computer machines to learn without being programmed. So instead, you show scenarios, which in this case would be data. And then using this data, um, computers can, like machines. So here I'm using computers and machines interchangeably, but essentially artificial thing, so artificial products. So think about robots, self-driving cars, chatbots, all of this, that ability to learn without being explicitly programmed. So deep learning is now the ability to extract patterns from data. And I'll show you they're essentially approximated, they're mathematical functions that learn features from the data. And here, features are characteristics in the data. So you can imagine like, like age. So if you're talking about like people, you can imagine features being things like age, height, color. Uh, yeah. So if you're thinking like an image, you can imagine features as, like the RGB component, like how the contrast of an image, the edges in an image. Or if you're thinking about a tree, you can imagine like an edge of a tree will be different from a four. So those are features, right? And you get them directly from the data. So the key point I want you to learn from here is that deep learning is essentially a bunch of function approximators. And I'll show you what neural nets are more deeply. And function approximators that can learn features directly from the data. And when you learn that, you're able to, so that will be machine learning. And then the ability for computers to mimic the behavior will be the artificial intelligence. It's not the natural or biological intelligence. Okay, so of deep learning is a perceptron. Perceptron is a neural net. Actually, this is not the simplest one, but like what you're seeing here is an input. I can show you here. So this is an input. So this is an input node, an input, another input, and this is an output. So what I'm saying is that a very basic neural network has an input. Uh, Actually, there's something that's missing here. What can someone? Does someone know what's missing in this, or what's not here in this? In this, what's missing in this neural net? Does someone know? Oh, someone is saying, please share your screen. Can you see my screen?
Yes, we can.
Uh, I think someone might have a problem seeing my screen, right? Like Sinabo. Can you see my screen? Oh, the guy is just not audible. I want to be very audible. Am I audible? Like, should I increase my volume or should I just tell me? Okay,
Yes,
am
Uh,
you
I?
are
Is it better?
audible.
yes, yes, it is better, Anthony.
Okay, I think
It
Chiba
is better,
Chiba
Anthony.
can't hear me.
You can just try
It's
to
better.
increase your
Okay,
voice. Yeah.
increase my volume. Okay, I'll do that. Thank you, Kip. Yeah, uh, awesome. Okay. I sound better. Okay. Please tell me. Yeah, I'll try to project more loudly. Okay, thanks. Yeah, thanks. So I was asking from this picture, what is there something that you think that's missing for anyone who knows some bit about like uh, uh, the simplest neural net? Does anyone has an idea about what might be missing here? Any guesses? Any guesses?
Maybe I can try, but what is missing in
Thank
the
you. Yeah.
whatever you is we're missing activation functions, which we're missing the activation functions.
Is it who's speaking? Who spoke? Thanks. That's very cool. Yeah. Actually, so yeah, I feel. Wow, you've seen ahead actually, because yeah, I'm yet even to introduce activations. Here, I'm just saying you have an input and an output. I think so. What's actually missing is a layer called hidden layer. So
Yes,
here,
yes.
so a simple neural net has an input layer, and then it has some hidden layer, and then it has an output. And I'll come more deeply into how we sort of compute like an output. But here, simply what you can see is that I'm multiplying an input and some sort of a weight, and then I'm adding a second input and another weight, an input and another weight. So that's this operation, essentially a linear operation. And then I'm adding some sort of a bias, so some sort of a noise, and that gives me an output. But I'll come. So let me show you what's missing. So this is a neural net. This is a multi-layer perceptron. It has 3 inputs. It has one hidden layer which has 1, 2, 3, 4 neurons and one output. So when you're thinking about a neural net, this is what you're thinking about: some input, some hidden layer, and some output. And the same you'll be thinking about. So you'll be thinking about the operations that happen here, and then so you pass in some data, and some magic happens in here, and this is magic, and then you get an output. Yeah. So, question: is this output linear or non-linear? So people say they have done a math course before, so I think that's not like super new, right? So can I get some guesses on the chart? Like, is that output linear or non-linear? Any guesses? Someone can type on the chart. Any chat response?
Okay, can I take a go,
Oh,
Anthony?
I'm not going to continue without that response. Yes.
Okay, since I'm from the diagram that you have shown, I am not seeing any activation functions and all of that. So I would say that the output is linear. And even judging from the formulas
Perfect.
that
Perfect.
you have used. So that's my
Thank you,
understanding.
Sam. Yeah. Thank you. I think, yeah, awesome. I also see many people say linear, and that's very correct. Yeah. So this output is linear. And why is it linear? Okay, yeah, there's like something that was giving it away, right? Because essentially, these are linear operations. So you see, this is this weight and this. Uh, uh, so this is a weight and an input, a weight and an input, a weight and an input, and then a bias. Then when you do that multiplication, you get an output. So as Sam has said, we still don't have an activation. So I'm going to now introduce activation. Yeah, I'm just So yeah, I mean, so the idea, the goal. Remember why we're talking about this is because the goal is the question we still have at the deep of our like deep down is how can we configure a neural net to learn such outputs? Uh, if you want to know this is a cat, that's not like you can fit a straight line. When you say linear, we are talking about a straight line, sort of like you can clearly classify things against the line. So like you can imagine I don't have a plane here, but like you can imagine a Cartesian plane, like an X and Y, and like you have points in there, and then you can sort of draw a line and clearly categorize those. So if you want to find out whether this is or a dog, like you need to add a few things. And I think some of the people have been alluding to activation functions. So like a ReLU, and I'll talk a bit about them down. This is another ReLU, and then you do some reduction, max 4, and then you can essentially create some nonlinearity. So the point I want you to take home is that a neural net is essentially a bunch of linear functions. I mean, it's a combination of just I think I'm not sure I'm saying mathematically correct, but like it's a bunch of linear functions which have been then have an activation function which brings nonlinearity. That's what I want you to take. And now I'll go deep. Yeah. So we need to. This is what I was saying. So we need some way to insert some linear mathematical operation into the model so that we are able to, get more you can classify more deeply. Like, you can be able to say, this is a cat or a dog. That's not a linear problem. And then these are activation. They're essentially mathematical operations. So some common ones are a sigmoid. The sigmoid, essentially, if you have an input, it transforms it in some sort of a form, that is between 0 and 1. If it's a tangent, this is a hyperbolic tangent, which takes it from, like -1 to 1. Or if it's a rectified linear unit, which is a ReLU, if anything is is less than 0, it's 0. And everything that's past 0, it remains to be that value. So if the value is 2.5, it's 2.5. The value is -2.5, becomes 0. And this brings nonlinearity. And why I want you to pay attention to this is just because nonlinearity is what will give us the ability to classify, to do cool stuff, because like many problems are not linear. Okay. Exactly. Yeah. So which one is used here? Which activation function is used in this example? Just let me get some shouts on. Okay, I'm scratching and you can't hear me. Okay, I will just try to be more audible. I don't like not to be audible. Yeah. Can I be heard now? Sorry about that. Maybe it might be network issue. Yeah. Yeah. Sorry, my NZ. I hope you can hear me. Can I get some responses about what you're saying now? Does anyone know what activation function is happening here from anything, any evidence that shows on the screen? Can Mayenzi, can you hear me? Can I be heard? I don't know.
Yes, Anthony, you can be heard. I can hear you clearly.
Awesome. Thanks. Okay. I see. So yeah, can I get some guesses, maybe from any information I have showed here on the slide that gives you some idea about what activation function might be used in this neural net?
Anthony, I think they have raised some hands, and maybe they are waiting for you to tell them as to how to
Oh,
proceed. Yeah.
sheesh. Oh, I'm sorry. I'm sorry. I think I'm waiting for people to type on the chat. I apologize. Is that better? I don't know. Yeah, yeah. Sorry. Oh, I think Shongwe and Tabani. Oh, sorry. I apologize. I think in my head I'm like I'm looking at the chat and I didn't see no responses, and I'm like, okay. I apologize. I think people wanted to talk. Uh, you know what? I'll give people a chance to actually talk at some point here. I know some exercises. Okay. Yeah. It's sigmoid, and this is an example that I got from some very good material. If someone really wants to read a little deeply, yeah, I'll share these slides, and hopefully you can click on this link. But it's a machine learning crash course. Yeah, by Google. Yeah, and this is a sigmoid, and what it does is just takes everything from 0 to 1, as we've said. Okay. Yeah, why not do fun stuff? So you know what? I wanted to click on this thing, and maybe I share this tab. I think also something I could do. I can also put this on the chart. Can I put it on the chart? Yep, I can. Yep, it's I thought we could tinker with the neural net right here on the browser, and we can't break it, so that's cool. And so here is a data set we can use. So it's like, well, what sort of a data set is this? Well, what is this property? It's like a cyclic, this is what I was saying earlier. It's not linear. You can imagine here, you can draw a line here and separate orange from blue. But good luck with drawing a straight line here. So you need some sort of non-linearity to essentially learn, the orange and the blue. Okay. And here are some things you have your input data. So like X1 and X2. So X1 might be the orange and X2 might be the blue. You see you have 4 neurons. It's the same. And this is one hidden layer. And then you have 2 outputs. Actually, you have 2 hidden layers. This is another hidden layer. And in this place, you can even add layers, you can remove them, and epochs. So I'll just quickly talk about this. So epochs is the number of times you look at the data not you look, the more the machine you train your. So if you have a data set that's 10,000 data points, your machine learning model looks at all the 10K data points. This is the training set. And then, how many times it does that, that's an epoch. And learning rate is, these things we can get deeply at there, but this is a sort of a regularization technique. So how well you train. And I'll get this. I think time is going, but I'll talk deeply. I'll show you where this comes in. And we've talked about activation functions. So this is at an H, for example. There's a sigmoid, there's the linear unit, and there's a linear activation. Yep. Regularization, this prevents overfitting. So you can have an L1 norm. So that's someone is mic is
Mankoba, can
on.
you please
Okay,
mute
and then
yourself?
you can have a classification or a regression problem. And if we play a little bit here, for example, and you can see some, test loss and training loss. I'll talk about this just a few minutes, but like that's how you you know see you're still like at 1,000 and sort of like this looks like it's trying to learn some representation, get some orange. It's still a hard problem. You can come here and see what it's outputting. You can see that it's like it's pretty cool. You sort of like start to see, you can see some of the ways it's trying to take shape. So it's a hard problem. So so normally what this is happening is what would be happening in a GPU, right? You would design how many neurons you want, how many features you want, and based on your data, and then you'd see your data many times. You decide on what activation to use, and many of these things you can change from one to another. It's a very experimental task, so you can end up getting something to work. Let's see. And you can see it's like the blue is coming. It's such a hard problem for this neural network set. And you can imagine it's just like up until 5,000 examples. So, I mean, so it's like we've gone 6,000 times through the data. So what we are using this task, thank you for the question. So the problem we are classifying, so you can imagine this being to know X1 and X2. So you can imagine cats and dogs, spam emails and not spam emails. And then, yeah, but you can imagine you have to, this doesn't look like it's going great, right? Like, see, so does anyone think about how we could make this small toy example work? Like, what are some canonical ideas to get this task going? Like, what sort of things can you do? Any random thoughts? I can just can type. Because like you don't want to train for so long. Some of the thoughts that could go on here is that you could have an activation function. You could have you could change the activation function, and you could you could add the neurons that go in. You see at this point, it's very hard for the model. At this point, it's super hard. It's super hard. Can I hear some thoughts about what people are thinking? Could be a good idea. Any thoughts? Are we in the room?
Anthony, can I take a go?
Yeah.
Yeah, so since I see that it's a classification problem, and I think it's not a multi-class classification problem, and that the range of which we are classifying is between -1 and 1. So I think I will suggest maybe we try and change the activation function. Maybe let me say that we can
I
use. Mhm. So maybe let me just say that maybe we can try to use the leaky value.
you're suggesting we use a real?
A leaky value, like a leaky rectified unit activation function.
Yeah, see, yeah. Uh, Actually, yeah, so that Ariki Lelu is a version of Relu. There's like another math trick that has been added to the Relu, and I think it could work also. But out of the options that we've got right here, is there any that you guys think could work? We could probably add just layers, right? Yeah, I mean, uh, I don't. You say we could, we could possibly just add like layers here. We could possibly just, add more layers so we can be able to run more. We can change the rate at which so slower or faster, like uh, you know, and then, for example, it could be lower, and then you could do a ReLU, as someone saying, like a version of it. Then, I mean, if you get the idea that there's an overfitting, you can try to regularize. But just, you know what? Because of time and all, I'll just let people play around, and then before we end the presentation, uh, I mean, we can see what someone has found to work really awesome. Yeah, and then like uh, that makes part of the assignment. Yeah, I thought at this point I'll just like get this 2 minutes video on us to watch and like get a recap before we do a quiz. So pay attention. Can you hear when I
Thus far,
is it clear when
Yes,
I play?
it is.
Awesome, cool.
we've developed great techniques for modeling linear relationships in data. Algorithms like gradient descent automate the process of finding the best parameters for a linear model. But what about modeling nonlinear relationships between features and the label? We've learned how to construct synthetic features like feature crosses to represent nonlinearities. But finding the right crosses is a manual process, which can require a lot of experimentation. Wouldn't it be great if our model could figure out these feature crosses for us during training? Incredibly, it can. Let's take a closer look at how. In our standard linear model, we take the value of each input, sum up the results, and add the bias value to get our result. We can think of this as a single combination of our inputs to produce the model output.
Anthony, please unmute your mic.
Yeah, the video is not audible.
Anthony, please unmute your mic. We can't hear anything. Anthony, can you hear us?
Sir Anthony, can you hear us? He might not be getting us.
I think just try calling him.
Hi, Anthony. Please please unmute your mic. We can't hear anything on the video.
Ah, damn. Could you? Oh, you didn't hear nothing. Oh, fudge. Okay. Let me try that again.
Thus far,
working?
we've developed great techniques for modeling linear relationships in data.
Is it hard?
Algorithms like
that
gradient
okay?
descent automate the process of finding the best parameters for a linear model.
Can people
But
hear?
what about modeling nonlinear relationships between features and the label? We've learned how to construct synthetic features like feature
Can you hear?
classes to represent nonlinearities.
Yes.
Is it? Can you hear? Okay, cool. Apologize. I think I'm just gonna.
Thus far, we've developed great techniques for modeling linear relationships in data.
Yep.
Algorithms like gradient descent automate the process of finding the best parameters for a linear model. But what about modeling nonlinear relationships between features and the label? We've learned how to construct synthetic features like feature crosses to represent nonlinearities. But finding the right crosses is a manual process, which can require a lot of experimentation. Wouldn't it be great if our model could figure out these feature crosses for us during training? Incredibly, it can. Let's take a closer look at how. In our standard linear model, we take the value of each input node, multiply it by a weight, sum up the results, and add the bias value to get our result. We can think of this as a single combination of our inputs to produce the model output. What if we added another layer to our model that recombined our inputs? This would increase the number of parameters in our model, allowing us to learn more about the interaction between features. This structure is called a neural network, and that additional layer is called a hidden layer. Could this architecture help us learn nonlinearities? Unfortunately, looks like we still have a linear model, just a more complex one. How do we learn nonlinearities then? Is there another kind of calculation that can come to our rescue? Neural networks solve this problem by introducing an additional calculation step when combining inputs, called an activation function. For example, after calculating the output, we can apply an activation function that transforms the output as follows. If the value is negative, return the original value. This simple function is called a rectified linear unit, or ReLU. Because this function has a nonlinear shape, inserting it into our neural network allows our model to represent nonlinear relationships. If we activation function before outputting the final value for each node in our network, our model can automatically learn the correct nonlinear relationship between features and the label during training. With enough layers, nodes, and activations in our neural network, we can approximate any function, including feature crosses.
Awesome. Was that clear? Did people? Hey, that's sort of like it's a summary of the neural net. I want us to get to a quiz, and then talk about and then a bit. Yeah, this is also like machine learning is deep. Like there are people who do PhDs on ML, like neural nets. So this is a very friendly intro. Yeah, but it's I hope it like appeals to your intuition. Yeah. So I'll just get into the quiz. Just write an answer on I think here you can. I think let's get people to talk. So let's get someone to sort of explain to us what the understanding of weights and bias is, like weights and bias. Someone can, I think at this point, someone can talk. Like my Ubongo, what do you think about weights and biases? When someone says weights and biases, what's your understanding? Okay, or someone else. Yeah. Someone can say anything, right? I mean,
Okay, I think I will take on the weight and biases, then I will leave the others to the others. So when we are talking of weights, we are just talking about as to how important each input is. Then a bias is just a constant shift of the output. So earlier you just present to us things called neurons, which basically performs just a symbol mathematical operations of which is a summation of the multiplication between the weights and the input. Then on top of that we add a neuron. So then we then have the input, then we have the weight, then we have the bias. So in just short, I'd say that the
you see,
weights.
yeah, that's
So just in short, I'd say that the weights just tells us as to how important each input is, and then the bias just it's just a constant that shifts the input.
thanks. Yeah. That's about right. Yeah. So as you should, weights, it's 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 the mathematical value that brain has, like how much weight it contributes to an output. The bias is just like that, and uh, yeah, it's the just on. It's actually a value as well that's added on uh, uh, so every layer has every neuron has every neuron has a weight, and then every layer has a bias.
Okay.
Does anyone wants to say something about what input and hidden and output layers are?
Okay. Can I try on the inputs, hidden layer, and output layers? Can
Please,
someone hear
yes.
me? Oh, can someone hear me?
Yeah. I hear you, correct.
Okay.
Yeah,
So
hear you.
what I got on earlier on about inputs layer. The inputs layer is more like the first layer of a neural network, right? Where it's like receives the data and trying to analyze or predict, and each node or in the inputs layer represents a feature of the data, right? Hello.
Yeah. I hear you. Yes.
Okay. Then continuing. What's the name? The hidden layer. Okay, hidden layers are I got that are just the complex representation of the data about data built, and these layers extracts features, patterns, and like relationships from the inputs data. So multiple hidden layers can be stacked like to learn increasingly abstract representations, and each node like in a hidden layer applies an activation function to the weighted sum of inputs from like the input or the previous layer. then going forward to the outputs, like where like you get the or generates the final prediction or classification. The number like of nodes like in the output layer like can somehow depend on like the problem, especially like binary in terms of binary classifications and like regression. So the output layer somehow uses an activation function suitable for the problem, or like such as a problem that is linear. I don't know if I'm making any sense.
Yeah. Thanks. I think that's about right. Yeah, you have like an input, a hidden, and an output layer.
Yes.
That's like the basics. Yeah, and then as you say, so the output will either be a regression or like classification. So an output. Hidden layers will be where the characteristic of the data is learned.
All right.
Okay, cool.
Okay.
Active. Thanks.
No problem.
Anyone wants to say something about activation and sigmoid function? And someone said, Fortune, thank you. Yes, Lenye, yes. I hope I don't butcher your name.
Hi.
Hi.
I think, can I try on the activation function?
Please go ahead. Yeah.
I think the activation function, I think it's like it introduces non-linearity into the model. Without it, I think then the neural network would simply be a linear regression model, regardless of the number of layers, which then limits its ability to learn the complex patterns in the data.
Nice. That's quite about right. Yeah.
Yes. It also helps in decision making to determine whether then the neuron should be activated or not. So that's what I have. I'm not so sure about
Awesome.
that.
That's cool. That's cool. Yeah. So activation is what brings non-linearity, and sigmoid function is a type of activation function. But what is a model? Thanks a lot. Yeah, someone said on the chat, input layer is the first layer that is put into a neural net. Then hidden is the middle layer. Exactly. Yeah. Thanks. I like that. Yeah. I like that. Yeah. As a BISA, I think that's cool. Yeah. So, anyone wants to say something about what a model is? Anyone wants to say something? Okay. Don't be shy. Just speak up, and there we go. Is there someone who is raising their hand and I can't see? I just call on people. Luzila Vilakati.
Malaza thatha yakho le baba.
Do you want to say what the model is?
Thatha lo
Oh.
mbuto wakho lo.
Thank you.
Thatha umbuto.
Yeah. Thanks, Hanifa.
Kuthi-ke
Yeah.
what is the
Maxwell,
model?
please. Yeah, thanks.
Buka Malaza lo munye uze
Is it
uyakuphendulela.
Maxwell who's raising their hand? Yeah.
Okay.
Let me try. I don't know whether everyone can hear me clearly.
Uyaphi? Okay, ngiyeva sis.
Loud and
Hello?
clear. Loud and clear. Can hear you. Yeah.
Thank you, Mr. Anthony. So a model, I'll say, is a smart machine that takes in input data, process it through several layers and learns the best weights and biases, then produces an output and so on and on. I don't know if I've tried to
Yeah,
explain it very well.
you did a good job. You did a good job. Thanks. Yeah, it's essentially that, you have like an input and then some processing and then an output. That's essentially a math representation of it. Thanks. Anyone wants to close up with what a neuron and neural net is? Any anyone wants to say something? Okay. Lenya, are you raising your hand or? Thanks, Kwawe. Neuron? Oh, thanks. Someone said it in the chat. The unit that processes inputs, apply weight. Awesome. Thanks. That's just about right. Yeah. Set of algorithms. Yeah. As you said, exactly. It's exactly what we've been talking about. It's like you have an input and an output, so that network is a of neurons. Thank you. Thanks. That's such a. So now that we've done with that, I thought we would walk through an example that I found to be very, very cool from an MIT course that I definitely recommend. And I'll just actually share that screen right now. So yeah, because let's just see how this course I think it explained quite well how how to, like in a very well intuitive example. So imagine you are taking a class and you're asking yourself, will I pass this class? And then well, you do have two inputs: the number of lectures you attend and the hours spent on a final project. So I mean, yeah, assuming that a final project has also definitely contributes to your grade, right? So if these are two examples, you can, what sort of a model can you, neural net can you, is this classification or regression problem? Someone can just shout. Yeah, because like this, you're just classifying, whether you pass or fail, because that's the quality. Yeah, so this is a classification problem. So what essentially happens is that you have a bunch of data, right? So you've taken data previously that shows hours spent on a final project and number of lectures you attend. And then this is an entry point of someone who passed, an entry point of someone who failed. And you might be wondering, if you're somewhere there, will you pass or will you fail? It's a very classification problem. And so essentially, you can pass this on a neural net. You have an input layer, you have a hidden layer, you have an output. So if you pass, this is your data point. This is how much, but actually, so 4, 5, so X is, this is the number of lectures you attended, and 5 is how many hours you spent on the project. So, if you have those, pass them through a neural net, then you get a prediction. But we can then find out whether you actually passed or failed, right? If you actually passed or failed, you're done with the course. So why is this? So you see that this doesn't do well, right? Like it's predicted to be just like way low. Almost it said like you failed. But actually, you passed. So what's happening here? What's happening here? Thanks everyone for answering the question. Yeah, classification, that was neat. Does anyone know what piece we've not talked about yet? Like we talked about, this is a neuron, this is the components of a neural net. So what haven't we talked about? We've already talked about the data. What these are last, well, these are pieces we've not talked about. Can anyone guess? Like, and we alluded to it when we talked about epochs, like the thing looking at your data. Well, what's that thing we didn't explicitly say? Any guesses? Any random guesses? Any guesses? Any guesses? Say, well, what do you, when you're showing a neural net or your data, what are you doing? You're essentially training it, right? Like, we've not quite talked about how training happens, right? Like, in a neural net, we've not deeply talked about how you train things. Like, how do you train? How much weight do you put on X1, and how much weight do you put on X2? That's the thing we alluded to as weights, because those things are learned when you show it many data points, and that's why in this case we've not trained anything. That's why we're predicting poor. So what we can do is actually train. And training essentially is you go through all your data, the first round, and then do a prediction. Compare it to actual value. So essentially, it's a loss function. It's a loss function. Loss, loss is, how much accurate. Loss is how much are you losing if you think about it, like in that sense. Like, this is this function of an input and weights, and then compared to like the actual value. So it's actually is essentially a difference. I predicted 0.1 and I wanted 1. So you essentially you want to make this loss as small as possible. And it's also called cost, incorrect predictions. So you can imagine when we said we have a bunch of data. So you have people who 4 hours. I attended 4 classes and spent 5 hours. Attended 2 classes and spent 1 hour. Spent 5 classes and spent hours, and on and on and on. And then what you do is show your model. So you have your data, have your model see all this data and how much they did. See, the model predicts 0.1, but that's not true because like it was actually 1. Look, someone 0.8. Actually, this person didn't pass. And then this was 0.6. They actually passed. You do like, so what you're doing, you're training the neural net using your data set. And then you're calculating the loss function and then propagating those losses back. I'll talk about backpropagation in a second. But this is the main concept. So you can, so you have an objective function, a cost function. It's essentially, for all your data points, you can calculate. And loss is just essentially the value that was predicted minus the actual value. Then you can essentially normalize it, just because some differences might be so large, they might be misleading. You normalize just to help training work well. And there are two, so the binary cross entropy loss. So that's a type of a loss. That's a type of of a function that it's essentially this formula. Like it takes the logarithm of the predicted value, multiplied by the actual value, and then you add that to 1 minus the actual value, multiplied by the logarithm of 1 minus the predicted value. It's like the intervals. You essentially want to reduce it as much as possible, so you have a negative. And this loss is implemented in some of these machine learning libraries, like TensorFlow, and this is by Google, and loss, and PyTorch. I think this came out from Meta. Yeah. And there are other losses. So for example, this is just actual minus predicted. It's a mean squared error loss. So you square the difference, and then you normalize it. And all of this you don't have to implement from scratch. There's a TensorFlow implementation of it, and a loss, and a PyTorch implementation of it. And all of these different, you decide on which loss to use based on your problem. Sometimes if you have many outliers or values that, and we're going outside very far, but the more you the field, the more it becomes clear which one to use, and sometimes you just experiment. And so the key question to ask yourself is, well, what's the problem you're solving, and what do you really actually want? So do you actually, often you want, yeah, but it's very dependent on the problem that you have. I see. Okay. Yeah. Is there any question at this point? We've talked about the basic neuron, the perceptron, and then we talked about activation functions, and then we've walked through an example where we have some data points of the number of classes someone attended and the number of hours someone spent on a project, and then we've tried to ask, will this new person who spent 4 hours and who attended 4 classes and 5 hours on a project, will they pass or not? That was the question we wanted to ask. Then we went through how we would train a neural net. So we would show a neural net a bunch of data, and we would minimize the loss. The loss, that is the difference between what the neural net is predicting versus what we actually know to be the truth, the label. And then this magic actually, well, when you do that for a couple of classify can actually find real values. So that's a regression problem. So what we've not talked a little more about is the training process. So that's what I want to show you. Yeah, we've talked about a loss function, but how we that we want to reduce the loss as much as possible. And here I'm being it's a very simplified way I'm talking about. At this point. But what I want, so the main point that I want you to go home with when you think about a training of a deep neural net is that you initialize a neural like what you saw, like with some so you have like some hidden layers, some output layers, and then you initialize some weights. So there are methods to initialize weights. And this is like how, so you can have a distribution of weights, like a normal distribution of weights. I think there are some other techniques to start with. You can initialize some weights. Then once you use those weights to get a prediction, then you can compute some gradients. So this is the way to know how much the change in different layers affect the output neuron. And so what happens is that you propagate that, so we're going next to talk about backpropagation in the next slide. But essentially is that you go back in every layer and you tweak a little. So you change things a little. And then you update the weights. So when we class in a project and the number of classes you attend, so that information will essentially, how much the model is getting the prediction wrong, that loss will propagated backwards. And then that's the backpropagation process. And then you end up having updated weights. Let me show you what I mean.
Imagine you're a teacher assigning your students a group project. Class, you say?
Is this clear? Can you hear the video? And I'll come to your question, Sibia.
Yes, we can.
Can you hear the video?
Yeah.
Yes.
Awesome.
I'd like you to work together.
Oh, sheesh. Sorry.
Imagine you're a teacher assigning your students a group project. Class, you say? I'd like you to work together to determine the kind of tree in the photograph. The students start sharing their guesses with each other, passing their ideas forward to the students in the row ahead of them, until they reach Jabari at the front of the classroom, who shares the final answer. It is a maple tree, Jabari proudly announces. You show the class a total of 7 different tree photographs, and the students correctly identify only one tree. So many wrong answers. Look at the difference between these two pictures, you say. Let's see if we can troubleshoot. Gasper, please lower your voice a bit so that Hao-Yu and Isabella's opinions can be heard. You proceed from the front to the back of the class, giving feedback to each row of students. It looks like Hao-Yu's answer was based too heavily on what Daniel told, not enough on what Fatima told him. Let's fix that. With your guidance, each student adjusts the relative strength of their contribution to the final answer. Good work, students. Now let's try this again. You show the class a total of 7 brand new tree photographs, and the students correctly identify 3 trees. That's much better, class, but we could do much better still. Working backward again from Jabari in the front of the class, back to the back row, you adjust the strengths of the students' individual contributions. Neural networks face the same challenges as your class. Neural networks use an algorithm called backpropagation to apportion blame to the different nodes. Instead of you adjusting student voices, mathematical formulas examine the various interactions between nodes and adjust the parameters. That is, the weight of each node. When loss is high, or the learning rate is high, backpropagation tends to adjust parameters more severely. As loss drops, backpropagation adjusts more gradually. Eventually, the model's parameters become as good as they can be. The resulting model can make more correct predictions. Although the students classified images here, the same backpropagation technique would work for any classification problem. Note, however, that image classification models often use a different type of neural network configuration. To learn more about building image models, check out the resources below.
Awesome. So just to reiterate, this seems to just appeal to your intuition, just how you just think about the training process, like that example of a classroom, and you're sort of like teaching them how to recognize some plant trees, etc. So I have about 7 minutes to just like conclude things. I wanted us to do a test, connection test. So who responds? So what I need you to do is this. I'm gonna share this link on the chat, and then this 7 minutes or so, you spend them on the the 5 questions, and then you hit submit, and then you tell us what you scored. So what you should see is this. When I share it, I will click on it. You should see something. You should see this. You should see this. So you should fill in these questions, number 1, 2, 3, 4, 5, and then you submit an answer, and then you tell us what you got on the chart. How does that sound? Did someone saying something? Yeah. So yeah, that's is everything clear? Like, does everyone? Sam, Betty, is everything clear?
Yes, yes, it is from my side. Although there's a
Hello.
yeah, it is clear from my side.
I think it
Although there's
is. And if anyone did not get it, please unmute and ask that they may repeat.
okay, thanks. Yeah, let's do this. Let's do this. And then after this, I'll share the call. We will go through the answers, and then I show you the example we had earlier, and then people can ask questions, and then yeah.
So, question, Anthony. Question,
Yes.
Anthony. Mm-hmm. How long have you given people
Yes.
for?
Yes.
I was asking as to how long have you given the
Yeah.
participants? Is it
Time. So up until 36. So 10 minutes. About 10 minutes. I'm sorry, I'm very unfair with the time, but so at so my I'm in East African time zone, and it's 12:27 p.m. So at 12:35, that 12:37 p.m. It will start to hope to see some people who have completed. Sorry. Congrats. I see some, not to give anyone pressure, but like, awesome. See some good things on the chat. Hey, congrats. Congratulations. Very cool. Very, very cool. Very cool. Let's give people 5 minutes and then, and then, but congrats. So some people who have finished, the gift of work is more work. Gift of good work is more work. So, just yeah, awesome. I'm happy to see people who are getting good scores. So if you've got a score, just head on to that link and get that link has very, very good definitions. So when you're talking about bias and when talking about weight, network activation functions. Damn, people are getting 5 out of 5. Congratulations. I feel like I'm pressuring people right now. Damn. Yeah, when you're done with the task, just feel free to look around. Yeah, I'm not sure whether Salman and Lenye have a question or yeah, you can type it on the chat or you can speak up.
Yes, thank you, Anthony. I'm sort of having a weak internet connection, but I was opportune to be able to join today. I really like the way you handled your session, I must confess, and I've been looking forward to it. However, I want to ask, is this session being recorded so that we can go back to it and just look at some few topics and resources and give you feedback some other time, please? I don't know if that's possible.
Okay, the session is being
Betty, have you been recording? I'm not sure.
yes,
Okay,
yes,
cool. Thanks.
the session is being recorded.
Okay, thank you.
Thanks.
Thank you.
Salman, please. Thanks, Lanya, for your kind words. Nice. So we just have about 2 minutes. Just wrap up. And then I think I will appoint the people who got 5 out of 5 to just, say something. So if you got 5 out of 5, just I can understand the last one, kindly help. Oh, you can't understand the last one, kindly help. Okay, we'll start there. Yep, so
Excuse me, Lenya, you had your hand up. Is it a question or you accidentally put your hand up?
I'm sorry. I think it was a mistake. I don't know. I didn't.
Oh, okay, it's okay.
problem. Okay, we are wrapping up. Okay. Yeah, thanks. Congrats. It looks like the last question, to be fair, we didn't talk about it. So, if you got 4 out of 5 and you failed the last question, it wasn't like clear to you, you know what? It's perfect. It's no problem. But we actually, you did very well. So let me, I think someone got 5 out of 5. Dunduzo. Do
Sorry, can you repeat that? Kind of having a network troubles. Can you repeat the question?
Sure. Look, would you like to just talk a little, like in a few seconds, about how you thought about the last question, like question 5? If you will. I'm just pointing on you because, like, I think you got that right. If you're in a position, you can say something. If not, oh, sorry, is Lenya trying to raise the hand or say something?
Not really. I don't know what's happening. I'm not raising my hand, but it's just there. I don't know why.
Oh, okay, no problem.
I'm still not getting what
You
you're
can turn
saying.
it off.
I'm still not.
You can click on the raise hand icon and then it will be done. Okay.
Okay, so because of time, I will just summarize. So, okay, no problem. So we didn't talk more. So we talked about a binary problem where you have x1 and x2, and you're trying to classify this. And then this question was asking you, I think, if this was like more labels. So you had, well, what's the question? You're training an image classifier model to predict dog breeds. So from a photo of a dog. So you're not like asking dog or a cat. The breed registry. So the model should successfully classify both pure breeds and mixed breeds. So that's a different kind of classification. So in this case, it's a one versus all classification. You're asking, this one breed. So is this a pure breed? Is this mixed breed? So the problem is multi-label classification. You're trying to predict a dog's breeds from a photo. So the output can be multiple breeds simultaneously. E.g., mixed breed dog. That's like, I don't know breeds of dogs. Like, I don't know, German Shepherd or whatever. Yeah. But that's different from binary, where you're saying A or B, X1, and that's also different from, so you can have multi-class, like you have a German Shepherd or another kind of a dog breed. But multi-label is that you can have, one or more classes simultaneously. So something can be mixed. It can be a little German Shepherd or a little something else. You can imagine like a Wikipedia article. It can be a technology article and still be in AI, or I don't know whether I made it clear or I confused you more. But you know what? There's like a very, very good, if you go back on, so you can see a neural net course on the machine learning crash course, and it has a very intuitive explanation. Yeah. Someone asked about two. Remember, we talked about a rectified linear unit. When if it's negative, it turns everything to zero. Otherwise, if it's positive, it remains the same. That's an activation function. Yeah, congratulations. Everyone did a good job. And I'm so proud of you. I thought I wanted us to walk through a code lab, but I think we won't have time. But this code lab is very well written. It has very good, like examples and like very well written. So I think I apologize that I didn't exactly manage them well because I would have wanted us to walk through it in this example. But I hope you've been able to sort of get a picture of how deep learning looks like. And you ended up doing a test and you did really good. So I'm super, super proud of all of you, everyone, for paying attention and, being involved. So I'll share these slides and someone can, click on this demo and, walk through this example and just keep learning, keep practicing. This is like, I feel like I touched the iceberg and I didn't really get in depth. Yeah, and like, please just, so I got a lot of these materials from this Clash course. I recommend it. And I really love the materials from this course. It's a Stanford course. And this is a very legendary course. It's a very old one, but it was taught by one of these now called godfathers of AI, people who started working on machine learning when it was not cool. And this is Andrew, he's a very popular machine learnist. It's a very good material as well. At this point, I'd just like to give people a chance to ask me questions or hopefully just get a sense of if someone learned something or, yeah, this place is just a moment now to hear from you. Just any question, any comments, any thoughts are welcome at this point. Yeah, I'm done. Like, I welcome questions.
Betty Makagonski.
Can I be heard? Can you hear me?
Yes, we can.
Yeah, I think you can ask me things about, I don't know, anything. Like maybe some, yeah, like apart, especially people who say they've not played with Gemini. I'm just, oh, I forgot something though. There was like something I wanted to show you guys before, but yeah. But I'd like to get some questions. You remember when I was telling you about this thing? So you can add different neurons and, can remember earlier we just had 3 neurons and 2 neurons here. And these are still 2 hidden layers, but we still have more neurons and more neurons. And you can see how neatly the model has learned to, distinguish from the orange and the, even remove this. Like the blue ones are neatly inside, it's a circular. You see just about 300 steps had some learning rate, regularization, and this was also classifying between orange and blue. It's pretty neat. Yeah. Any questions? I believe that people can go to Gemini.com and they can play with Gemini. And you can actually use, some people can get to some pro versions in some African countries. Yeah. So you can just look around and see.
Anthony, can you hear me?
Correct, yes.
Okay, nice. With regard to Gemini, I have a question. Compared to like other LLMs like GPT and Cloud and the Meta LLMs, is there may be a framework or a standard that you can suggest on fine tuning or on prompt optimizations under Gemini? Like
When you're using it on the web, or when
like let me just
are you
say that
thinking about using it?
let me say that when I want to fine tune it to a specific task, is there any best practices under Google that you can recommend? I don't know if I was audible.